Okay, so let's start with what are threads? Now, threads are a really, really old idea.
Where the distinction matters more will be more specific. Okay, many languages are dogmatic about the solutions they offer for handling concurrent problems. For example, Erlang has
I'll just live.
Okay, so let's start with what are threads? Now, threads are a really, really old idea. They were the first reference that anyone I could find um, was all the way back in 1967 on a programming manual for the OS 360, which was an IBM room-sized mainframe that was built around the idea of doing multiple things at once. It could batch process through huge amounts of data. Threads come all the way back from there, and they were difficult then. They've been getting gradually easier as you build better abstractions around them. They're an old idea. They're probably not a completely solved idea. They've been getting better all the time. Prior to threads in Unix, the usual way to make a program run concurrently in the background was to call fork, which makes an entire copy of your process. One copy exits, one copy keeps running in the background, detached. Forking is kind of an expensive process because you literally take a copy of the whole program. With copy on write, forking became a lot cheaper. Now, a thread is actually kind of similar because a thread executes in the same memory space as the rest of the program. They still get their own entry in the operating system scheduler. They still have their own call stack. They still have their own state, and they're preemptively multitasked. So when a thread is executing, at any time, literally any time, unless you've marked what's called a critical section, the thread might be interrupted by the operating system to switch context. At that point, the operating system grabs a snapshot of your execution state, so instruction pointer, register state, and similar, saves it, goes to whichever thread's taking control, restores their setup, pushes it back. And this can happen as frequently as every 16 microseconds, particularly on Intel chips and AMD chips, x86, x64. Context switching is quite cheap now. On older ARM chips, it was pretty horrific, which led to some of the initial ARM systems going entirely with cooperative multitasking. Now, we're not going to be talking about async today because I've done quite a few webinars on async. I've done quite a few webinars on safety in general. Threads are heavier than async. You don't want to have tens of thousands of threads. You can have tens of thousands of async tasks, but modern Linux is really, really smart. And a lot of the complaints you hear about threads, for example, your scheduler slows way down because you have so many threads, are much less true than they used to be. Linux is really good at marking this thread is waiting for this operation, this network operation, this disk operation. Let's not schedule it yet. Much better than it used to be. Macs and Windows, not quite so good, but still really good. And last I checked, I could spawn about 30,000 threads on my Linux desktop in the office before I started getting error messages. So threads are an old school system. They are the fundamental building block. All of the async systems out there use threads. They're built right into your operating system. And Rust is basically exposing your operating system's API for creating threads. It's adding very little. This is a thin wrapper. You're not losing performance by using the Rust representation of threads. You are using your operating system's threads. So why are they difficult? There's a meme being going around for a really, really long time. And this was the first tweet I could find of it. A programmer had a problem. So he thought to himself, I know, I'll solve it with threads. Has now problems to he. I've also seen that with he now has 12 well problems. And what does that mean in practice? It means that now you've taken something that was quite easy to reason about, a program that is running from top to bottom. So you're going step 1, step 2, step 3, but now you've got all these threads that are running all at once. And just like you sitting at your desk, if someone comes along and interrupts your train of thought, you context switch. Now you pay them some attention, or hopefully you might just ignore them. And then you have to context switch back to your program. And as most programmers will tell you, there is nothing worse than an unscheduled meeting in the middle of your busy time to throw you off. And that's exactly the same issue with threads, is that you can be interrupted at literally any time. If you haven't remembered to lock your input-output thread, you end up with your printed out of your busy time. And as most programmers will tell you, there is nothing worse than an unscheduled meeting in the middle of your busy time to throw you off. And that's exactly the same issue with threads, is that you can be interrupted at literally any time. If you haven't remembered to lock your input-output thread, you end up with your printed output has now problems too. Well, each of those executed in a different order, and so gained access to the I/O at different times. What's coming out doesn't even make sense. And with threads, you don't have a lot of control over the scheduling. You don't get to really say this thread will go now, this thread will go now, unless you start tying them together with sync primitives. The operating system handles that for you. And so threads can be hard to reason about. As humans, we like to think in terms of doing one thing at a time. That's pretty normal, pretty common. Don't feel bad if you're one of those magical people that can do 2 things at a time. My wife can. I really don't know how she does it. It also gets difficult because you're sharing data between threads. And this can be dangerous. In previous webinars, we've talked about data races. We'll have a quick look at one in a moment. But basically, if two threads concurrently access the same piece of data and both try and change it, it's very unlikely, unless you've got some sort of locking primitive, that the answer you get is what you thought it would be. So you can be quietly corrupting your program in the background without ever knowing it. But thanks to threads, you're corrupting it really fast. It can be confusing too. If you've gone with everybody's old favorite style of code where you have lots of global variables shared between threads are writing to them all over the place. Good luck ever debugging that. It's also very easy to make spaghetti because now you have threads that are all running independently. If they're all accessing different parts of the state of your program, it's almost impossible to figure out why did this variable gain this value. As Bill always likes to say, the best code is the code that you can read easily from top to bottom. He's absolutely right. And so when you're threading, it's quite important to make sure that you avoid making spaghetti, avoid confusing yourself, and absolutely avoid danger. And lastly, threads are difficult because they don't always provide the magical speedup that you think they will. It's actually surprisingly easy to write a threaded program that is slower than the single-threaded version because CPU cache tends to keep a blob of memory, read through it, access it very fast. If you suddenly need to synchronize that between all your CPUs, all your memory accesses just became a lot slower. And sometimes the 16 microsecond context switch between threads is actually slower than the amount of time it took to sort your million numbers. I mean, some of the sorting functions are incredibly fast. Threads aren't always going to take something and make it magically faster. Sometimes using the threads actually imposes more overhead than doing it the simple way. So you have to make sure you think about, do I need threads before you dive into this? Okay, so first example, we've got, I called it an innocuous looking piece of C++. I don't know how many of you use C++, but my experience from using it professionally from 15 years was that the innocuous safe looking stuff is usually where I'm going to have trouble. So we make a thread, and you'll notice the C++ syntax is a lot like the Rust syntax. There's a reason for that. Rust originated with Grayson Hoare and a team at Mozilla. You'll notice the C++ syntax is a lot like the Rust syntax. There's a reason for that. Rust originated with Grayson Hoare and a team at Mozilla getting fed up with C++ and the problems it was causing them and trying to come up with something better. We make 8 threads. Each of them prints hello world and the counter from 0 to 7. And then we join the threads, which we'll talk about in a moment, but this is wait until the thread has executed. Looks great. You run it. There's a snapshot of the output there. Hello world, hello world, hello world 02, blank space, hello world 6, hello world 3, 1. So sometimes we've got them, we're getting the full output we want. Sometimes we're not. The first line, you can see that actually the printing process was interrupted by other threads before it even finished formatting everything else. It looks nothing like what we expected. It's completely harmless. We're not doing any damage here, but it's probably not what you wanted. It's worth noting that Rust, when you do print line, acquires a lock to standard output, so we won't do this. But this is a blessing and a curse, because it's a blessing in the sense that your threaded program printing out isn't going to give you gobbledygook. It's a curse in that it means that print line is actually quite a bit slower than you might expect it to be. So if you write a program whose main purpose is printing huge amounts of text, you need to jump through a couple extra hoops to get the lock before you print all the text, because otherwise you're actually acquiring a mutex and releasing a mutex, which we're going to talk about in a moment, for every line that you print. So once again, Rust is making it a little safer. At the same time, Rust makes it a little slower here unless you know what you're doing, so you have to be careful. Data races. One of the big things that Rust promises is that you won't get in data races. And we, if you go to the Art and Lab YouTube channel, I have a couple of entire videos where I have talked about this in huge detail, so I'm not going to go into it very heavily today. But here's a simple Go program that runs 100 threads, each of which adds to a counter and then prints out the total, and you'll get a different answer every time. And the reason for that is that writing to incrementing an integer isn't a one-step task. It loads from memory, it adds to it, it stores it back into memory. And remember how threads can interrupt you at any moment? Well, it's quite possible that they'll interrupt you while you're loading, while you're adding, while you're storing. And so when you've got 2 threads that simultaneously load, each of them adds, and then all try to store, it's very unlikely that you're going to get the answer that you expected. Now, quick note to the Go programmers out there, turn on your compiler's data race detection. It will spot this problem. And now, quick note to the Go programmers out there, turn on your compiler's data race detection. It will spot this problem and won't make your life miserable. If you have code in production that you haven't checked for that, go ahead and check it, because this is one of the most common problems out there. Uber reported that they found tens of thousands of these bugs in critical code. Rust can't protect you from data races between services that call each other over the network. It will make sure that you don't have data races inside your program. Okay, so jumping into the meat, we will go ahead and make a threaded hello world. And so we start off, pull in std thread. Std thread is the most basic interface to talking to threads in Rust. It's been in Rust since before 1.0. It is an almost exact mirror over your operating system's thread system. So we call thread spawn. What that does is it launches up your operating system thread system, creates the thread, passes it. This is a closure inline function. You can also pass it a function name with no parameters. And we're just going to print hello thread, print hello world outside of the thread. And then we're joining. And what joining means is when a thread returns, its join handle will stop blocking. So you can wait on the thread to join. Be sure that the thread is executed. If you forgot to join, it may or may not print hello thread. It will always print hello world. Joining makes sure that that thread is completed before the main program completes. And they expect something went horribly wrong. Usually join handles won't give you an error result, so you usually see them unwrapped or expected, but there are times that it can. So this is relatively straightforward. In the 3 lines of code, you've created a thread, done something, waited on the thread. It's about as simple as it gets. So let's start to talk about different ways, different approaches to threading. So we looked at std thread. It is the most basic thread creation system. Okay, so the upside of std thread, straightforward, pretty foolproof because you've just got the one simple command. It's ideal when you want to make a thread and have it do something independently. There's also a slightly convoluted thread builder system that you can use if you start to need to customize how much stack it allocates. Much to my surprise, basic Rust did not have priority and CPU affinity built in. There are crates for that. The reason for that turned out to be that they're so different between platforms, and not every platform even has those concepts. It couldn't be in the standard library and have the standard library still be cross-platform. So let's look at the big downside of that. Capturing scope with regular std thread can be painful and can be really confusing to the newcomer to Rust. So this is a very similar program to the Go one we talked about. It's not quite the same thing, but we create a mutable counter. Mute means mutable. It also means compile time mutex, which we'll talk about in a second. We create a vector of handles. The join handles we talked about. When you call .join, the handle that you wait on is called join handle. We make 8 threads. We push each thread. So we push each thread and we go into each thread, push the join handle for each thread, spawn it, count to 1,000,000, increment the counter. So this is a lot like the Go code, except we've just got 8 threads instead of 100 of them. And down at the bottom, we're doing handles. I used into iter as opposed to iter. The only difference there is that it consumes the iterator going through because we're never going to use it again. So this will not compile at all. And the reason it won't compile is that the error message will even tell you. It tells you that you are attempting to access the you're attempting to access the already mutably shared counter again. So this will not compile at all. And the reason it won't compile is that the error message will even tell you. It tells you that you are attempting to access the you're attempting to access the already mutably shared counter. That's the database protection kicking in right there. That's the borrow checker. And so this is the same example I used in the previous webinar. Your Rust rules with the mut keyword, mute, are quite simple. You can either have as many immutable, read-only accesses to a variable at the same time as you want, or exactly one mutable reference. So you are not allowed to compile code in which more than one part of the program at a time might be changing a variable. It simply won't compile. This is what you will see when you try and make a race condition. So we solve that by using an atomic. That sounds good, right? That's what we always say in classes, what I told you in the last one. And so this is the same program, but I've replaced counter with an atomic. You'll notice it's no longer mutable, even though we're going to be what I told you in the last one. And so this is the same program, but I've replaced counter with an atomic. You'll notice it's no longer mutable, even though we're going to be mutating it. We're going to talk about that in interior mutability. We still make the vector, we still make the spawns, we call counter fetch add, and now we get a truly bizarre error message. Function requires argument type to outlive static. It then even suggests adding the move function, which is really bizarre because it's no longer mutable, even though we're going to be mutating it. We're going to talk about that in interior mutability. We still make the vector, we still make the spawns, we call counter fetch add, and now we get a truly bizarre error message. Function requires argument type to outlive static. It then even suggests adding the move function, which is really bizarre because you'd be moving your ownership of your atomic to one of the threads, and then the next threads won't work. So what on earth is going on here? Now the problem is that std thread has no way of knowing if the thread is going to complete before the main function. Yep, we've got a join there, but the compiler cannot be 100% sure that something won't go wrong. Join is fallible, and this caused all manner of issues when Rust first came out. Like, how on earth do I have a local variable, access it in a bunch of threads, work with it? And the answer is they added scope threads to make this easier because solving the halting problem is extremely hard. It's practically impossible in a full, complete language to prove that different parts of the program will ever terminate and will ever terminate in the right order. And depending on the operating system you're on, sometimes a child thread may end moments after the main thread. So technically, Rust is technically correct here in the sense that you might, for just a very brief moment, try and access some data that isn't valid anymore. In practice, it's not really a problem, but Rust is doing its very best to help you. Arguably, it's trying a little too hard to help you. Okay, so we use a static variable. You'll see this in a lot of the early Rust around 1.0. Static variable is initialized before main runs, always deinitialized at the very end of the program. So now the compiler is happy because your static variable will outlive your code. And once again, we're technically correct, and this will give the right answer. But static variables become a problem when you start having static variables in functions, calling the function over and over again, because the lifetime of the static variable and the invocation of the function are not always the same. So this won't give you the results you expect when you're starting to write complicated programs. So this works, but it's not really the right answer. Now, for this particular problem, the best option is to make use of the join handle. Because join handles are not just for waiting for the end. You can return a value from a thread, and the join handle receives that value. So now we find my mouse cursor, we create a local variable, local to the thread, created inside the thread, it's not shared. We increment the counter, we return the counter. And so when we join, we can take those values, add them up. Downside here is we've added 8 additional additions to our program. Upside is we've made our program a lot simpler, and most of the time, combining the results at the end isn't going to kill you performance-wise. But the huge upside for me is that your program is now a lot more readable. It's not relying on static variables, which are effectively global variables. You have something nice contained, but it's still not the best way to approach. So where thread really shines is for what I call a detached thread. That is one that runs pretty much independently. Examples of that would be timers that need to fire on a periodic cadence, doing something nice. Network I/O threads to talk to other processes, even interacting with hardware interrupts. And the actor model is pretty much built around this. So not long after REST 1.0 came out, and enough of us whined about the difficulties of accessing local scope variables, scope threads were added to the standard library. And we're going to have a look at how to use these. They make it much easier to access local data because the lifetime is guaranteed. It is absolutely guaranteed that whatever threads you create in a scope will terminate at the end of that scope. Joining is automatic unless you actually want to return data, in which case you still need to read the join handles. This is perfect for those times where you have a big batch of data, you want to spawn off a bunch of threads, process really hard, squeeze the results back to one place. Very, very common pattern, particularly if you're doing anything in the scientific or numeric world. Now, the downside is that this is more verbose, and I have fallen afoul of this one. Don't forget to use the scopes that you created. Threaded scopes originate in the round library, which we're going to be talking about in a moment. Okay, so with a threaded scope, you'll notice this is pretty much the same program. We've got our atomic counter, just like we did before. But instead of spawning with std thread, we're calling thread scope, and it expects a closure, which will receive one parameter, the scope. And when you spawn, you don't use thread spawn, you use scope spawn, because you're telling that scope spawn the thread within your scope. And now we can safely access the shared variable because the lifetime of the program is now absolutely deterministic, and the rest library, the rest compiler can absolutely be sure that none of these threads will outlive the scope. All of this code is actually in the Ultimate REST class that I teach also. This is great in terms of giving you a nice, easy way to break up large amounts of data when you need to, process it all at once without jumping through hoops, without having to clone parts of it, generally make a mess. REST giving you the tools you need to easily divide it up into chunks, with even a chunks folder function if you're working on a vector. Work on it in pieces divided between your CPUs, and be 100% sure that you're not going to segfault at the very end of your program mysteriously because your thread outlived your main thread. Lastly, on this section, let's talk about Rayon. The Rayon is almost as old as Rust. If any of you have used Intel's threaded building blocks for C++, that was a lot of the inspiration for it. It's a nice C++ library to make threads a little less painful to use. So the upsides of Rayon is that it's really, really easy in most cases. Performance is fantastic, and if you have an algorithm that readily divides up to be parallelizable, Rayon can often allow you to write parallel code with very little effort. The downside is that you don't have as much control over the process. So if you're writing something really timing sensitive, really complicated, that has to interact with lots of other moving parts, Rayon may not be for you. But a lot of the time, Rayon, these sit idle until there's work to do. And we'll talk about the magic for how to do that yourself a little later. Rayon doesn't think of things to do as threads, it thinks of them as tasks. So in this respect, it's sort of a halfway house between async and threads. And a lot of the time, if you're doing a computational program, but async is the logical way to think about it, Rayon is the good bridge between the 2 points. Roland asked if we can prefer threads over async in Rust. I'll talk about that in detail at the end, but Rayon really does provide a good halfway house between the two. I personally recommend async for really high performance input-output. If you're network bound, your program spends a lot of time waiting on other things like databases, waiting for the network. I recommend threads when computation speed is your primary issue. And don't forget, you can always mix the two together. Okay, so where does Rayon really shine? Making life easy. It's great for, I have this one calculation, I need to go faster. Rayon really doesn't shine if you've already got a complicated threading system. And I went ahead and put it into a range because Rayon, by default, use Rayon Prelude Magic 40. The bad news, Rust's ownership rules still apply in a threaded environment. In fact, it's worse than that because Rust's ownership rules partly exist because of threaded environments.
Because I think we are. But no bells and whistles today, unfortunately. Let's see. All right, it looks like we are live.
It was neat. Oh.
So, I'll just say hello real quick. For those of you that are joining in online, welcome. For those of you that are in the room, thanks for being here. Thanks for putting up with my nonsense. And we didn't get the meetup page updated because I didn't get the title until yesterday, and then I was at work today, and so.
It's just in time compiling. It's really
Don't bite
good.
the hand that feeds you.
But what's our title, Michael?
Why Rust is worth it. Fearless concurrency no matter the paradigm.
All right, cool. Well, if at any point you find this to be useful or interesting or entertaining, or you just like his shirt, give it a like, and let's get rolling.
Cool. Yeah, I'll just introduce myself. I am Michael Edlinger, aka M. Kedlinger, a username that I made when I was 10. You can basically find me anywhere that I have an account under that name. I am a tech enthusiast and software engineer. I did a couple of internships for AWS when I was in college, and then I worked for this little startup called CallForce here in Utah, and now I am at Ancestry. I've been using Rust for about 2 years now. It's kind of become my de facto personal project language of choice. And I've tried other languages like Zig or VLang or Nim or Kotlin, but I continually come back to Rust. And I find that it is a fantastic language.
You use it at Ancestry.com?
Yeah, approximately 0% there. It's a little bit of a bummer. Oh, and that actually reminds me, I'm going to try not to just like absolutely blast through and like talk really fast. So if you have a question and I'm not looking at you, please interrupt me. I'm trying not to go like crazy fast. So yeah, please.
Why did you drop your first I?
Yeah, it's my initials and then my last name is the username. That was my thought
The E's in there
process.
twice, actually.
So it's MKE, so my middle name, K, and then Edlinger.
He was K too.
So first title, and you might ask, you know, worth it? Like, why would you imply that Rust is not just the best all the time, every time? This is a Rust meetup. What are you trying to say? And yeah, I would say that I'm not even just implying that Rust isn't always the best. It's just not. But I don't know if anybody's trying to argue that. But the purpose of this talk is to kind of look at when it is, because Rust is an incredible language. And there are some strengths and weaknesses that we can look at. Like, for example, I am doing the Advent of Code this year, which for anybody who doesn't know, that's like 25 problems, one each day from the 1st of December to the 25th. And they're just little problems. And in this scenario, I've been using Rust, and it's actually kind of been painful because, you know, these aren't problems that need like long-term maintenance. They're not, performance isn't really important, and the complexity of Rust is almost wasted on these problems. I don't know if that's taboo to say, but
These are problems like, you know, reverse the letters and do little simple
exactly.
things.
You look at this palindrome and
Things
whatnot.
that use at work all the time.
Yeah, exactly. So it's not that important, but when corrected, so you can see by a little tagline here, when correctness and performance aren't always paramount, but when they are, Rust is killer. And so that's what we're going to explore today. Why is Rust so good in these scenarios? Sweet. So here's what we're going to be doing today. We're going to be looking at a kind of toy problem. It's called the 3n+1 problem, also known as the Coalesce conjecture. Veritasium has a really cool video. Have you seen it? It's really kind of a fun toy problem. It's super simple. The only reason it's interesting is because it's deceptively simple. In the mathematics world, it's something simple enough you'd think there's a formal proof for it. However, there is not. As just a way of introduction to what this problem is, and the simplest way that I can say it is that for any positive integer n, the algorithm shown there will eventually reduce to 1. So if I chose 8, essentially the conjecture is that 8 will reduce to 1 if you, whenever the number is even, divide it by 2, and whenever the number is odd, multiply by 3 and add 1, and then take whatever that is and keep going until you hit 1. And the conjecture is that all numbers, all positive ints, will eventually reduce to 1.
But the number of iterations is unpredictable.
Exactly. The entire nature of the problem is quite unpredictable, which is why it's still a conjecture. Even though it's been, I think, brute force up to 2 to the 68th. So it still holds true for everything we've tried. The problem doesn't really even matter. It's kind of a toy problem to show these different things that we're going to try. We're going to explore doing the Coalesce conjecture for a set of ints with a couple different paradigms. First, we're going to try single-threaded, just a really simple implementation. Then we're going to start moving to multiple threads. And then we're going to look at what it would take to go to multiple computers, aka network service, aka asynchronous Rust. And we're going to look at what the characteristics might look like for each of those. Any questions so far? I'm trying not to blast. Cool.
So far, so good.
Sweet. So we can look at our single-threaded implementation first. I chose to do in JavaScript. JavaScript is pretty simple, and there's a pretty good chance, at least most of you have written JavaScript before. This implementation is super simple. We can just see that I'm looping over from every number from 1 to 1,000,000, and for each of those numbers, we put it into the while loop, and we don't actually even test anything. The idea is that if this program completes at all of the numbers were indeed valid, a valid part of the Coalesce conjecture. And we're going to try to quantify some of this. So I'm going to plug this into Hyperfine, which is it's a benchmarking tool. That's pretty nice. If we run,
What is this?
this is me SSH'd into my server at home. What's the
outside?
like
What is the
like this?
presentation? Is this just Dmux plus?
You asked what's that?
Yeah, so this is Biobu. This is the multiplexing for my terminal, is Biobu. And this is how I can switch between terminal windows that are on my server. And then the actual presentation software is called Look at Me. And it's just kind of this terminal
Okay,
presentation
so you're
software.
running Look at Me inside of Tmux.
Inside of Tmux, over an SSH connection. So it's a, yeah. Yeah. Anyways, cool, it ran. And it ran pretty fast. It averaged about 1.4 seconds. So in the single-threaded node implementation,
To check the first million?
to check the first million.
Wait,
Yep.
you said it average, so it mean it ran it a bunch of times?
It ran it 10 times.
Oh, okay.
And that's what Hyperfine does. Because otherwise we wouldn't be that sure whether or not the one run I do is that representative.
In the naive implementation in Rust or the finely tuned implementation? Versus
Faster.
We're just doing it for
Very simple to performs. We'll go and build it. Seems I've built it before. And Nope. Awesome. So we did it in about 115 milliseconds. This is about an order of magnitude faster. And this might be something you guys expected. It actually wasn't. I wasn't expecting it to be that much faster. So I actually put the code into Godbolt to see what the actual assembly was, just because I thought maybe the loop got optimized away somehow or something. And no, it's just that much faster, which is awesome. But it actually kind of hurts a point that you'll see that I've tried to make a couple times, which is that often garbage collected languages are kind of good enough. The Debian Linux distro, they have a team that they have dedicated to this benchmark game, and that's what they call it. And they just implement a couple problems in multiple different languages. It's by no way authoritative, but it's kind of an interesting way to kick the tires. Go ahead, yeah.
Oh, nothing. Nothing. I was stretching.
Oh, sorry. So what we can see here is that for the most part, this is kind of what we'd expect. Rust is 100% of the time faster. But what we might not expect it is, while sometimes Rust is many times faster, like for binary trees, we'll see that like Rust versus JavaScript, it's roughly 7 times faster. But we can also see some cases where it's not that much faster. Like in the pi digits benchmark, Rust goes in about 0.7 seconds, where Java is in about 0.9, which is only about 0.2 seconds off, or kind of comparable. It's not too crazy. It's not too far off. And so why do I bring this up? The point is to look at Rust and say, well, where does it bring benefit? It has some increased complexity that comes from being a kind of harder language to learn. Where does it like really take off? And and the answer is during concurrency, when you're trying to do things fast and correct at the same implementation of something that's actually parallel. Let's try to use some threads. JavaScript parallel, which would to be essentially enforce a code correct. So that we might wonder is this, we print a number, is compiles what we output.
Yesterday and all of today.
All the as with many browsers, so astutely saw is that this is not going to run deterministically. It's going to vary wildly affected behavior that you were looking for. People have threads, and for each of these threads, we're going to loop over, grab a number from next, make sure it's not greater than up2, print it, compute the collection conjecture, iterate next. So much the same thing. And we might wonder, is this program correct? Obviously no, but are we going to have the same issue? Or is this going to behave the same way? And no, it's not, and the reason it won't behave the same way is because it won't even compile. Rust is smart enough to look and say, you are trying to borrow next in this loop, and you're borrowing it multiple times, one for each thread. That is going to create a race condition. We're going to have a problem. Rust won't let us get to the runtime to see how poor it is. And something you might have noticed too is in Go and in Rust, I iterate next after I compute the collection conjecture. And I do that because if I put next, the iteration of next, right after I pull num equal to next, the Go code actually behaves. I wasn't able to reproduce the race condition a single time. So you could be tricked into thinking you have correct code. You could have something in production, and you might look at this code and you could say, well, this is, I mean, obviously we saw it very quickly, like anybody could see this. But tell me that when you're looking at 100, 200, a million lines of Go code, and you get a race condition, you could end up having something that sneaks in there, and in a million lines of code could be very difficult to find. So what does Rust provide for us to save us from this? There are essentially 3 different things that I think really set Rust apart. First, there's ownership. Ownership is essentially 3 rules, which I have shamelessly copied from the Rust book, the excellent Rust book. First, each value in Rust has a variable, and that variable is called its owner. There can only ever be one owner at a time for a given value, and when the owner goes out of scope, the value will be dropped. There's also rules for references. There can be one mutable reference, XOR any number of read-only references, so either one or the other. And we can kind of see here in this little code example that I wrote up that we have this value, a vector of use sizes, right? So that's the value, and the owner variable is the owner of that value. On the next line after that, we have a mutable reference that we are taking, and that's also fine, but when we get to the third line and try to get a read-only reference, then we are going to see a problem. That would violate the rule of exactly one mutable or multiple read-only references. The reason that this is important is it helps answer some questions that the Rust compiler needs to know to prove that our program is correct, which is who can mutate a given value, and who's responsible for cleaning it up, right? In our Go implementation, who can mutate a value is a very important thing to know if you're going to be trying to mutate it from multiple threads at the same time. There's some guarantees you want around mutation from multiple threads. And then who's responsible for cleaning things up? This problem is related to double free memory issues or use after free memory issues, where you don't want those. Those are memory safety issues that Rust tries to protect us from. Anything so far? I realize I'm looking at the screen a lot, so. Traits are not too unlike interfaces that you would see in Java or other programming languages. I'm not super familiar with Go's idea of interfaces. But anyways, traits are not too unlike that. But we're not really focusing actually on that idea of traits. I'm thinking more of something in Rust called marker traits. And these marker traits are managed entirely by the compiler. For example, you can't implement any of these traits for types that you create. They're implicitly defined. And they represent some properties of types. And they help the compiler ascertain whether or not your program is correct. Specifically, when it comes to concurrent code, there are 2 traits that are very important to us, the sync and send traits, both of them being marker traits. The send trait essentially answers whether or not the type can be safely sent across threads. And an example of a type that is send is an atomically referenced counter. These values actually are, I guess maybe it's better explained from the counter example. Something that is not send is just a normal reference counted value. And the reason that this would not be send safe is that it can't atomically synchronize the reference counts. You could think of a situation where two different threads are trying to decrement the reference counter, and since they don't do it atomically, you could reach a race condition where something is trying to be double freed. Then we also have the sync trait, which essentially is kind of more abstract, but essentially describes types for which it is safe to share references between threads. And this type manages whether or not something can be safely mutated for multiple threads. An example would be a mutex, which we're about to look at, and actually make a multi-threaded example that's useful. Something that's not valid is the Rust's cell type, and that is something that provides interior mutability, not too unlike the mutex, but it has no synchronization, it has no ability to, yeah.
So you said that these are automatically generated? These
Yeah.
fields? And so you can't find them yourself, and the compiler just decides for itself if it can use it or not?
Yeah, basically. So there are some types that are in the standard library that Rust provides that it just knows implements these traits. And there's some general rules that Rust can say, that it can look at and say, well, if your type is in a type that is sync, then I'm just going to call the whole thing sync, and it can all be moved between. I'm going to be honest, I'm not sure entirely.
And I'll sync, then it will be send and sync. Send and sync cells aren't.
A little bit hard for me, but it seems to mostly make sense.
It syncs like, I think I want to use an immutable reference.
Needs to clean it up. Probably my favorite. I think this sets Rust apart a lot, at least from a lot of the programming languages I've used. RAII stands for resource acquisition is initialization. And a good way to explain this is actually by looking back at our Go code. So what was wrong with our Go code? We didn't have a lock. We didn't have a mutex. We had no synchronization between our threads or our Go routines. And a way that we could have fixed that is by defining a mutex lock, locking before we access and mutate next, and then unlocking it when we're done with next.
So,
Yeah, go ahead.
just for reference, the proper way to do this in Go would probably be to use a channel.
I've heard they like channels a lot, yeah.
Yeah,
They like channels.
I've heard that.
I think that's true, and Rust is
No,
the
it's-
problem, so.
Yeah,
Okay.
Rust also
I
does.
think that's architecturally a better approach.
Channels orchestrate, mutex is serialized.
Just do a range of 0 to 1 to 9, and just start your own.
Man, it'd be terrible if that was an example later.
Open currency like this is like channels. It's just a abstraction layer across the.
Yeah,
system,
I'm actually
whatever
familiar
it
with
is. So that's why you would lean towards it in Go. I know there's only like 2 things that you can do in Go to like actually do this, but one of them is weight group.
Yeah. And for the most part, you might think that this is kind of contrived that I chose this example, and it is, actually. I chose it on purpose to be able to do the RAII comparison. So,
It can be done. A junior programmer will find a way to do it.
I believe it, I believe it.
Yeah, we will.
Yeah. And so besides these things, you might look at this code and say, what's wrong with it? Because it's technically correct. I mean, it will do what we want, right? The output would be what we expect. And really, there's nothing fundamentally wrong with it. But the issue that you could find with this is that we can misuse it. We can cause a race condition. You can acquire the resource next without properly initializing the environment for it, without properly locking the lock. So in this case, resource acquisition is not initialization. It doesn't. We can acquire without properly initializing things. And yeah, this code could compile, as we saw, just as well without the mutex. Go won't save us. Things are a little different in Rust. For this type of definition, I'm going to try to go with the latent pointer. We'll see if it's worth it. In Rust, the mutex that we create here, we can kind of mostly ignore the arc for now, but the mutex that we create actually encloses our value, our unsigned 64-bit int. And if we want to access whatever this int is and mutate or do anything with it, we're going to have to take this mutex and call the .lock method. Otherwise, we have no way of interacting with the U64. We have to call the .lock, and it will return something that's called a mutex guard. Upon acquiring this mutex guard, the mutex will be locked, and the only way that we can interact with this U64 is through the next guard. As long as the next guard is in scope, as long as we have the ability to access the next variable, this U64, this mutex will be locked. The only way to unlock this mutex will be to drop the next guard, and therefore have no access to the U64, no ability to mutate it. You could almost say that by acquiring or locking, we have properly initialized everything that's expected. And it's not to say that this is impossible to misuse. Deadlocks are still possible, but memory corruption certainly is impossible. And race conditions and memory safety issues are not going to happen with this paradigm.
And we don't even have to worry about unlocking.
And we don't even have to think about it, unless we want to, as we see here. Unless we want to. This is just me editing our previous examples to add the lock and to make so we actually see how this performs. This code is much the same except for adding the lock, and let's see how this works. So we're building it, and then we're going to run it in Hyperfine to see how it performs. The answer is very fast. So this implementation is able to run in about 132 milliseconds. It is not slow. But if we compare it to how Rust behaves, we might want to look at this code. This is basically, for the most part, the same, but we can actually see this code is exactly what we saw in the previous example. And something that you'll notice is that I have chosen to put it in its own scope. You'll notice I say that the lock will only ever unlock when next guard is dropped. And I could wait until the scope naturally ends here, but that means that I'm going to have to wait for the whole coalesce computation, and I'm no longer using the next guard. So I can actually put it in its own scope. This will ensure that it's dropped here and before we do the
And it's
computation.
acting the same with the go, or unlocks right after.
Exactly, much the same. You could also just call drop on this. I guess it's a stylistic choice. So sweet, this is much the same. Let's take a look at how it performs.
Faster.
Yes, indeed. a good bit faster.
Half it.
Yeah, a little bit more than half, but yeah, this is quite a bit faster. Not having a garbage collector is very fast. But this isn't the only thing that it affords us, like what Daryl was talking about. We can use confidently third-party libraries like Rayon. All the code that I wrote here, basically all of it, with the Rayon library could basically be condensed down to these 3 lines. And we can be confident that it will be safe and fast and excellent. Stay excellent.
If you have Rayon, sure, for station logo.
Cool. That concludes the parts that I am actually okay at.
Do you run Rayon code benchmarking?
Yeah, sure, you have Rayon.
No, actually I didn't. I wonder... I don't know how it would perform.
Touch a
Yeah.
file.
You guys want to see it? Okay, let's go and...
We want him to run
Yeah, that's
I don't know how it would perform.
touch a
Yeah.
file.
You guys want to see it? Okay, let's go and...
We want him to run
Yeah, that's just different, not
the
term.
Rayon code. to
I
see
do.
if it's any faster.
Let me...
Oh, yeah, we totally have run Rayon code.
Yeah, let me see if I can find it really quick.
And then we should do channel implementations. Does that, I assume Go has a non-locking channel implementation, right? I mean, it's so based on channels, it's got to.
Non-locking? That's a default.
Non-locking.
Oh, non-locking.
Yeah, it doesn't use interior locks. I mean,
Let's
locking
see.
channels don't.
I'm going to... How can I get to this really easy? Okay, sweet.
What channels though? Crossbeam? Crossbeam library? That's the kind of channels you should use in Rust. Not the standard library ones.
Correct.
They're made by the same people.
Okay, sweet. Yeah, I actually do have the ability to check. Let's see.
That's almost down to the libraries.
Crossbeam's good stuff.
Oh, I don't know if this is... Yeah. Okay, so there's 2 potential things. You'll notice this is actually quite a bit slower. I suspect that there's 2 different things. I actually only have that code written as a test. So maybe there's some
Don't
unfortunate...
do it in release mode.
Yeah.
You can change your test to run release mode. There's a
Oh, it probably built for the first one. Okay. Okay, that's far more comparable, actually. Wow. Well, compared to what we were experiencing here, right? So we had 74 milliseconds. This one's 84. That's comparable. I mean, it's still faster than our Go code, so that's cool. I also wonder, something that you might notice about what Rayon has to do is it actually fills out, it takes that range and it fills it out into an array, I think, to cut up between its work stealing workers. So I think that there's a cost associated with that.
there is a bit of overhead to how Rayon works.
Yeah.
So
So,
convenience.
but the convenience is excellent, and we're going to use
All
it.
that overhead of 10 milliseconds.
Cool. Yeah, now we're going to go into async land. This is kind of a speed run. This is a rough introduction of services. If we want to have a network service, as like a simple introduction, we can look at something that is roughly comparable, which is a synchronous and an asynchronous example that do basically the same thing, and then join on them. An answer to a question I had is it really that much faster? How much faster is it really? And this is actually an answer to a question I had is it really that much faster? To me, how much faster is it really?
So
A lot faster. Yeah, it actually kind of shocked me. I just made a little test that essentially does nothing but go over a loop of 10,000, and for each iteration of the loop, it creates a thread and joins it. That's all it does. And the async example literally just creates a future and awaits it. That's all they need to do. Threads took 357.
Spawn 10,000 threads. What's the stack size for thread and Rust?
If your features didn't do anything, they might have been optimized out. Rust has
Yeah.
fancy features that literally don't do anything anyway until they need to do something.
Yeah.
you cheat.
Very possible. Very possible. I would. I played the. I didn't compile in
Target
Tart.
footprint for 10,000 threads with a stack for each one of those.
A lot.
Significant.
Two megs per something like that.
It's only one thread at a time, one after the other, synchronously. Right?
That's all at the same time.
These are not concurrent in the way that I've written it. Yeah.
Black is kernel, and
Right? To do. And, okay, fine,
Yeah.
do we know it's correct, but I can optimize all the stuff out and I'll say.
So Levi's got a comment. He says Linux threads are cheap these days.
1 second.
If you want to take
I think what make sure the
iterate it.
It'll do that for loops.
Does anybody remember? Oh, every time.
Down this path.
All right. Let's. In the terminal or on this? Oh. Still a bit. I think. But
They seem to longer.
No, microseconds.
It's microseconds.
No, compared to the last time you did.
it did because it was
Oh,
taking
That's a
20.
good sign that it actually did something.
Hey, there we go.
20 to 700 is like leaps, 100.
Yeah. So I now I even feel stronger about the point. Yeah. Yeah. So sweet. Let's actually look at it as a async collats service. Async's so cool. It's way fast. Amazing. Wow. Not 20 microseconds fast though. That's honestly
So
about being able to async with something like that.
First one solved. They could maintain 10,000 connections at one time.
somewhere.
Came out. Only longer than
The future trait is part of this actually executes these features or tasks, and that's called an executor or a runtime. This is what polls the futures, continually progressing them. And there is not an implementation in the standard library. There's no blessed implementation. This is kind of up to you to find one that fits your needs.
Is it standard?
Yeah, so there's Tokyo. It's by far the most popular currently, and
So
it's
look at the timelines, how standard versus Tokyo doing.
I've never been concurrent much of.
Thread stack size is 2 megabyte by default, but you can set it to what you want. So I imagine the kernel will want you to use at least one page, typically 4K.
well, I think in what is it for GNU Linux? I think the default has been for your starting thread 8 megabytes.
Right.
So when you spawn a new thread, that's runtime dependent. But when the system starts like a thread or a program, like before it gets anything else, I think it's handful 8.
Supporting that small stack.
Yeah. Cool. Yeah, and then we have
Starting thread is different, not under Rust control.
Huh?
The starting thread is different. It's not under Rust control.
Yep. At least that's my understanding. We also have the async and await keywords. They essentially desugar down into some state machine of futures that the executor can use. There are some pretty cool articles that talk about what async await actually desugars to. That's above me. I don't know that. Cool. So we're going to kind of speed run actually making a call out service, because async honestly could have been its own talk. But kind of made sense as like the tail of this one. So maybe this is a nice intro to get us curious enough for whoever talks next, and maybe even talks about async request and tackles that. Some brave soul who's braver than I am. So to make a service, we're going to take in a couple dependencies. We can't get away doing async without them. We're going to use a simple gRPC service. So Tonic is going to be our gRPC server. It manages a lot of that. Prost is going to generate some of our Rust bindings for our protobuf definitions. We're going to use Rayon to actually do, just to make this build.rs. Essentially what this is doing is compiling our service.proto to actual Rust.
Welcome back, Rust gang. If you're new here, my name is Bogdan, and this channel is all about the Rust programming language. If that sounds appealing to you, make sure to hit subscribe for weekly Rust content. Today, we're starting chapter 16 of the Rust Lang book, and it's titled Fearless Concurrency. One of the goals of the Rust language is handling concurrent programming safely and efficiently. Concurrent programming is when different parts of your program execute independently, and parallel programming is when different parts of your program execute at the same time. These two concepts are closely tied. So for simplicity, for the remainder of this chapter, when you hear concurrent, know that it means concurrent and/or parallel. By leveraging Rust's type system and powerful ownership model, a lot of concurrency errors are able to be caught at compile time. Because of this, you're able to write code that is free of subtle bugs and is easy to refactor without introducing new bugs, which is why Rust uses the term fearless concurrency. Because Rust is a lower level programming language, it has various solutions to handle concurrency problems, and we'll explore those solutions throughout this concurrency series. So with that background, let's go. An executed program you can have code is ran within a process, and the operating system. In most current operating systems, an executed program's code is ran within a process, and the operating system manages running multiple processes at once. Within a program, you can have independent parts that run simultaneously, and the features that run these independent parts are called threads. Splitting your program's computation into multiple threads can improve performance because multiple parts of your program are running at the same time, but this also increases complexity. Because threads run simultaneously, you don't have control over the order in which different parts of your program are executed, which leads to some unique challenges. One such challenge are race conditions, where threads are accessing data or resources in an inconsistent order. Another challenge are deadlocks, where we have two threads that are both waiting for a resource that the other thread has, thus making both threads wait indefinitely. Lastly, because execution order is non-deterministic, bugs can appear that only happen in certain situations and are hard to reproduce and fix reliably. Rust attempts to mitigate the negative effects of using threads. However, it's on the programmer to be thoughtful when designing their program for a multi-threaded context. Now, there are two main types of threads: one-to-one threads, also called OS threads, native threads, system threads, etc., and green threads, also called user threads or program threads, etc. Many operating systems provide an API to create new threads. One-to-one threads mean that when you create a thread in your program, it maps to an operating system thread. So there's a one-to-one mapping. Many programming languages provide their own special implementation of threads, which we call green threads. Green threads do not have a one-to-one mapping with operating system threads. So you can have 20 green threads that map to only 5 operating system threads. This is why we call the green thread model an M-to-N model, because there are M green threads that map to N operating system threads. Each model has its advantages and trade-offs, and the trade-off most important to Rust is runtime support. By runtime, I mean the code that's included by the programming language in every single binary. Rust aims to have an extremely small runtime, in fact, almost no runtime at all. Now, the trade-off is sacrificing features, because the more features we include out of the box, the larger the runtime will be. Because green threads would require a larger language runtime, Rust only includes one-to-one threads or OS threads in its standard library. However, if you would like to use green threads with the trade-off of having a larger binary, then you could use crates that provide such functionality. Now that we've talked about threads in the context of Rust, let's jump into creating some threads in code. Here I have an empty main.r. To create a new thread, we're going to call the spawn function on thread, and we're going to loop through a range of integers. Also need to import duration. Outside of our spawn thread, we're also going to loop through a range of 1 to 5 and print the number. Here you can see we're printing out the number and letting the thread sleep for 1 millisecond. By default, every program through a range of 1 to 5 and print the number. Here you can duration. Outside of our spawn thread, we're also going to loop through a range of 1 to 5 and print the number. Here you can see we're printing out the number and letting the thread sleep for 1 millisecond. By default, every program has one main thread, so in this case, we're letting the main thread sleep for 1 millisecond. Also, thread sleep here just means that we're going to pause execution of this thread for a specified amount of time. To summarize, we've spun up a thread, and within the thread, we're going to count from 1 to 10, and for every number, we're going to print the number and let the thread sleep for a millisecond. To summarize, we've spun up a thread, and within the thread, we're going to count from 1 to 10, and for every number, we're going to print the number and let the thread sleep for a specified amount of time. We're letting the main thread sleep for 1 millisecond. Also, thread sleep here just means that we're going to pause execution of this thread for a specified amount of time. To summarize, we've spun up a thread, and within the thread, we're going to count from 1 to 10, and for every number, we're going to print the number and let the thread sleep for a millisecond. In our main thread, we're also going to loop from 1 to 5, print the number, and let the thread sleep for a millisecond. Let's run our program to see what happens. Here we can see we got number 1 printed from our main thread, then number 1 printed from our spawn thread, number 2 from main, number 2 from spawned, 3 from main, 3 from spawned, 4 from main, and then we have 4 and 5 from our spawn thread. Note that the output might look different on your computer because, again, the execution order is non-deterministic. Also notice that the main thread finished printing all of its numbers. We had a range from 1 to 5, so we printed 1 to 4. But the spawn thread didn't finish printing all of its numbers. The range was 1 through 10, but we only got to number 5. And this is because when the main thread ends, the spawn thread is stopped no matter if it finished executing or not. Next, we'll look at how we can modify our code to allow the spawn thread to finish execution. The first thing we'll do is store the return value of the spawn function, which will be a join handle type. Then at the end of main, we'll call handle.join, which will wait for our thread to finish executing. We'll also need to call unwrap because join returns a result type. Calling join will block the thread currently running, which in this case is the main thread, until the thread associated with the handle, which is the spawn thread, terminates. Blocking a thread means that the thread is prevented from doing any further work or exiting. Let's run our program again to see how the output has changed. As you can see, the two threads alternate in execution until we get to the end of the main thread, and then our spawn thread is allowed to finish executing by printing out the rest of its numbers. Now let's see what would happen if we take this handle.join call and move it right after our spawn thread is created. Because we called join right after our spawn thread was created, the main thread will wait for the spawn thread to finish executing, so we print 1 through 9 before printing out the numbers in the main thread. Small details such as where the join method is called can affect whether or not your threads run at the same time. Next, let's talk about using move closures with threads. Up until this point, when we spawned a thread, the thread didn't depend on any variables outside of the thread. But let's take a look at the following example. We have a variable called v in the main thread, which is a vector, and then we spawn a new thread, and inside the new thread, we want to print out the vector we created in the main thread. But as you can see, we have some red squigglies here indicating on a new thread, and inside the new thread, we want to print out the vector we created in the main thread. But as you can see, we have some red squigglies here indicating a compile time error. And if I hover over, you can see there are a few errors, one of which states that the closure may outlive the current function, but it borrows v, which is owned by the current function. Rust sees that v is being used inside our closure, but it's declared outside of our closure. So Rust will infer how to capture v. And because v is only used in this printline statement, Rust will infer that we only need a reference to v. However, this is a problem because Rust doesn't know how long the spawn thread will run for, so it doesn't know if v will always be a valid reference. Imagine if after spawning a new thread, we call the drop function on v. If we were allowed to write this code, then there's a possibility that when we run our program, we would spawn this thread, immediately switch back to the main thread, drop the value v, then switch back to the spawn thread, at which point v would be invalid. Because Rust doesn't know how long our thread will run for, Rust doesn't allow us to take a reference to v inside the closure. And if we hover over this red squiggly here, you can see it gives us a hint. And the hint states, to force the closure to take ownership of v, use the move keyword. In chapter 13, we learned about closures and the move keyword. If we put the move keyword in front of our closure, we're telling Rust, don't infer that the values inside our closure are borrowed. Instead, what we explicitly want is to move values inside the closure, or have the closure take ownership of the values. After specifying the move keyword, we no longer have a compile time error. And that's because now v is moved inside of the spawn thread, which means it can no longer be used inside of main. If I try to call the drop function on variable v again inside of main, you'll see we get a compile time error, which states that we cannot use v after it has been moved. That's it for this video. If you found it useful, make sure to tap the like button. And if you want to see weekly Rust content, make sure to hit subscribe. Also, Welcome back, Rust gang. If you're new here, my name is Bogdan, and this channel is all about the Rust programming language. So if you want to see weekly Rust videos, make sure to hit subscribe. Also, I'm going to be releasing a Rust cheat sheet very soon, so if you want access to that, make sure to click the link in the description. In the last video, we started chapter 16 of the Rustling book titled Fearless Concurrency, and we learned about creating threads. In this One increasingly popular approach to ensuring safe concurrency is message passing, where you have threads or actors passing messages to each other which contain data. The Go programming language has a slogan that summarizes this approach. Do not communicate by sharing memory, instead share memory by communicating. One slogan that summarizes this approach. Do not communicate by sharing memory, instead share memory by communicating. One tool Rust provides to enable message passing concurrency is something called a channel, and it's included in the standard library. Channels are analogous to a channel of water, like a river or a stream. If you put something like a rubber duck or a boat on the stream, it will travel downstream to the end of the waterway. A channel in programming has two halves, the transmitter and the receiver. Going back to the river analogy, the transmitter is the upstream location where you would place the rubber duck, and the receiver is the downstream location where the rubber duck will end up. One part of your code calls methods on the transmitter passing in the data you want to send, and another part of your code is listening to the receiver for arriving messages. The channel is said to be closed if either the transmitter or the receiver half is dropped. Once you're familiar with channels, you can implement things such as a chat system or a program in which many threads perform part of a calculation and one thread aggregates the results. Alright, enough talking. Let's see how channels are created in code. The first thing we'll do is bring the MPSC module from the standard library into scope. MPSC stands for multi-producer, single consumer. In Rust, the way channels are implemented, you can have multiple producers of messages, but only one receiver of messages. To create a channel, we'll call the channel function on our MPSC module. Channel is going to return a tuple, which contains the sender and receiver. So let's extract both of those out into a variable. Here I'm destructing the contents of the tuple into two variables, tx for the sender and rx for the receiver. Tx and rx are traditionally used in many fields for transmitter and receiver, respectively. Next, we're going to spawn a thread and use our sender to send a message. First, we'll need to bring the thread module from the standard library into scope. Next, we're going to call the spawn function to spawn a thread. Lastly, we'll call tx.send. Lastly, we'll call tx.send, passing in our message, and then unwrap. Notice that in order to use our sender to send a message, we need to move tx into the closure. If we remove the move keyword, you'll see we get an error, which states that it's not safe to share the sender between threads. Notice that we also call unwrap after send, and that's because the send method returns a result type. If the receiving end has been dropped for some reason when we try to send a message, then send will return an error. In this case, we call unwrap to panic in that case, but if this was an actual production application, you'd want to handle this case more gracefully. Next, let's use our receiver in the main thread to receive a message. We'll create a new variable called received, and that's going to be equal to rx.receive, in this case, recv for short, .unwrap. Then we'll just print the message we got. Our receiver has two useful methods, receive and try_receive. The receive method will block the main thread's execution while it waits for a message or a value to be sent down the channel. The receive method returns a result type. If we have a value, then we'll get the value. However, if the channel closes, then we'll get an error indicating that no more values are coming. The try receive method, however, will not block the main thread's execution. Instead, it will return a result type immediately. The result type will be an OK variant holding the value if a value is available, or it will be an error if no values are available at the time. Try receive is useful when you want your thread to do other work. For example, we can have a loop where every so often we call try receive to see if there are any new messages, but otherwise we let the thread do other work. For this example, we're using the receive method for simplicity because the main thread isn't doing any other work. By the way, when we're calling the send method in our simple program, we're passing in a string, but we don't have to pass in a string. We can pass in any type we'd like. All right, let's go ahead and run our program. And as you can see, our main thread got the message hi. Next, let's talk about ownership rules and how they relate to concurrent code. Ownership rules help us prevent errors in our concurrent code. As an example, let's see what would happen if we tried to use our message variable after we've already sent it down the channel. If we were allowed to do this, it would be problematic because we would send a message to another thread and then afterwards we could potentially modify or drop the variable. Luckily for us, we get a compile time error. And if I hover over, you'll see the error states we cannot borrow a moved value. This is because when we call send and pass in our value, send takes ownership of the value. So as you can see in this example, the ownership rules prevent us from doing something dangerous, which is modifying or dropping a value after it has been passed to another thread. Next, we'll modify this code to pass multiple messages to prove that our code is running concurrently. Instead of having a single message, let's create a vector of values. Then instead of sending a single message or value, we'll loop through our vector and send each message. We'll also let the thread sleep for 1 second after each call to send. Lastly, instead of calling receive on our receiver once, we'll use a for loop to get all the messages passed down the channel and print them out. Notice here that we're not calling the receive method anymore. Instead, we're treating Rx as an iterator. Every iteration will have a value that we pass down the channel, and when the channel closes, the iteration will end. Let's go ahead and run our program again. And this time you can see we're getting messages from the spawn thread with a 1 second delay. The last thing we'll talk about is creating multiple producers to send messages. Currently we have one thread that sends messages. However, let's say we want to have 2 threads that send messages. So let's go ahead and copy and paste this code. For the second spawn thread, we'll also change the values. Notice here that we get a compile time error, which states that we cannot use the tx variable because it has already been moved into the first spawn thread. To fix this, let's scroll back up to the top and create a new variable called tx2 equal to tx.clone. This will give us a new sending handle, which we can use in our second spawn thread. Now we have 2 threads that are passing messages down the channel to the main thread. So let's run our program so we can see that the messages from each thread are being sent non-deterministically. Note that the output might be different on your machine, and also when you rerun this each time, the output could be different as well. That's it for this video. If you enjoyed it, make sure to hit that like button, and if you Welcome back, Rust gang. If you're new here, my name is Bogdan, and this channel is all about the Rust programming language. Today, we're continuing our series on fearless concurrency in Rust. Last time, we talked about transferring data between threads using message passing, and in this video, we're going to talk about transferring data using shared state. You can think about shared state concurrency as one-way data flow. One thread passes a message to another thread, and then that receiving thread now owns the data. With shared state concurrency, on the other hand, we have some piece of data in memory that multiple threads can read and write to, and Rust gives you the flexibility to pick between these different approaches. So with that background, let's get rusty. The first thing we'll talk about are mutexes. Mutex is an abbreviation for mutual exclusion. And mutual exclusion means that you have some piece of data and only one thread can access that piece of data at any given time. To achieve this, mutexes use a locking system. When a thread wants access to a piece of data behind a mutex, it'll signal that it wants access to that data and acquire the mutex's lock. The lock is a data structure that keeps track of which thread has exclusive access to a piece of data. Once a thread has acquired a lock on a particular piece of data, no other thread can access that data. Once the thread is done with that piece of data, it can unlock the data and allow other threads to have access to it. Now, mutexes have a reputation for being hard to manage because you have to remember 2 rules. One is that you have to acquire a lock before you have access to data, and 2, you have to release that lock when you're done with the data so that other threads can have access. Now, this is a pain point that might lead people away from using this approach, but fortunately, Rust type system and ownership rules guarantee that you can't get locking and unlocking wrong. Let's jump into an example by creating a mutex. The first thing we need to do is import mutex from the standard library. Just like with many other types, to create a new mutex, we call the associated function new and then pass in the data we want to store. All right, next let's access the data in our mutex. First, we'll create an inner scope, then we'll create a variable called num, and it's going to be mutable. And we'll set that equal to m.lock, so we're acquiring a lock, and then we'll call unwrap. Here we call the lock method to acquire a lock, and this will actually block the current thread until that lock is able to be acquired. Now, when we call lock, it returns a result type, because if there's already a thread that has a lock to that data and that thread panics, then calling lock will fail. And in this case, we call unwrap, which is saying that if lock fails, then panic. Notice here that the type system is making sure we call lock, because m is not an integer, it's a mutex that holds an integer. So we can't directly manipulate that integer until we call lock. After calling lock and unwrap, we get a mutex guard smart pointer, whose deref trait points to the inner data of the mutex, which in this case is the integer 5. Also, mutex guard implements the drop trait such that when mutex guard goes out of scope, then it releases the lock to the data. This means releasing the lock will be done automatically for you, so you don't have to remember. All right, now that we got a mutable mutex guard, let's go ahead and manipulate the underlying data by using the dereference operator. Then at the end of main, let's go ahead and print m. Next, we'll run our program. And as you can see, m now stores the value 6. Next, let's talk about sharing a value between threads. We'll create a new mutex that holds the integer 0, and then we'll spin up 10 threads that each increment the value by 1, so at the end we'll have the number 10. First, we'll import thread from the standard library. Then we'll add a for loop, and inside the here we're creating a variable called handle, which is going to be a new spawn thread, and within the spawn thread, we get a lock to counter, and then we increment our counter. We also use the move keyword to move our counter variable into the thread. We'll talk about the red squigglies in just a second, and then after handle is created, we append it to our vector of threads. After creating our threads, let's join them all to the main thread, and then print out the result of counter. All right, that completes our program, but let's go back to the error we saw above around the move statement. If I hover over, you'll see that the error states we cannot move counter because it has already been moved in the previous iteration. What we want here is to allow counter to have multiple owners. And if you recall from chapter 15, the way we did that was using the reference counting smart pointer. So let's go ahead and wrap counter in the reference counting smart pointer. First, we'll import the reference counting smart pointer here. Then inside our for loop, we're going to create an idea, but notice here we get an error. And if I hover over the red squigglies, you'll see that it states we cannot pass the RC smart pointer safely between threads. The RC smart pointer gives us the functionality we want, but unfortunately it's not thread safe. So what we want is something exactly like RC, but thread safe. Fortunately, the Rust standard library has the atomic reference counting smart pointer, which is exactly what we want. Atomics are a concurrency primitive, which you can learn more about by looking at the standard library documentation. For this video, all you need to know are atomics are like primitive types, except that they could be shared across threads. So let's update our example to use the atomic reference counting smart pointer. First, we'll need to update our import. And then everywhere we use the RC smart pointer, we're going to change it to ARC. We can also remove this unused import, and just like that, our program is compiling. Let's go ahead and run our program. And as expected, the result we get is 10. You might have noticed that counter is immutable, but we're able to get a mutable reference to the value that it holds. And that's because mutex uses interior mutability. In the same way that the refcell smart pointer allows you to mutate a value that's inside an RC smart pointer, the mutex smart pointer allows you to mutate a value inside the arc smart pointer. Also note that the refcell smart pointer comes with the risk of creating circular dependencies, and the mutex smart pointer comes with the risk of creating deadlocks. We won't be discussing deadlock mitigation strategies in this video, but if that's something you want to see, leave a comment down below. The Rust language itself provides few concurrency features, but it does give you the building blocks to create your own concurrency features or use concurrency features written by others. Two basic concurrency concepts provided to you as building blocks by the standard library are the send and sync traits. I won't be going into those traits in this video, but if you want to see a future video diving deeper into concurrency, leave a comment down below. Alright, that's it for this video. If you enjoyed it, make sure to leave a like, and if you want to see weekly Rust content, then make sure to hit subscribe. Also, I'm going to be launching a Rust cheat sheet, which you don't want to miss out on, so if you want access to that, make sure to click the link in the description. And with that, I'll see you in the next one.
Hey guys, my name is Trevor Sullivan, and welcome back.
I can see myself. Okay, that's gone. Futures concurrency in the future. I'm Yash. I work at, my hand got cats. Microsoft. I've got cats. That's very important. This is Chashu. She was eating from my hand up until like just now. There's a treat here, but she's like no longer interested. So maybe she'll make an appearance later. And this is Nori, sitting in a box. And this was them together in our last apartment, doing what they do best, which is asking for food that they're not allowed to have. And then look what I do. Yes. Maybe you know me like, what might you know me from? I helped create Asyncstud once upon a time. I am responsible for... So we are talking about futures and async and Rust because it started in 2015 or maybe 2008. Kind of depends on how you start counting. But Std future today in the standard lib kind of looks like this. There's like a couple traits and like 3 functions and like
we create a stack allocated string that contains our kind of unparsed
Do not share memory by communication. Do not share memory. Do not share. very simple. Let's you can just say mutex, and you have to just like normal text that's new. That's I32. This is basically the text card. So for you to be able to use it, let's say let m is equals to so you have to see m dot log. You have to lock it then on wrap because there may be some error. Let's say now say m star m because it's a pointer plus equals to 1. You definitely increase it. Then if you print m here, it's definitely increased to 43b. So it's immutable, so basically muted for that shit. It's okay, because it's implement debug. Let's see. Okay, cargo run. Yep. So that's that. But let's say we want to across thread. So much of it. Let's create a new thread. Thread.spawn. Let's create a spawn. Alright, so see data. And let's say we want to let m
I'll just say hello real quick. For those of you that are joining in online, welcome. For those of you
You never win. Wish we could just all build the things in one thing. I know, right?
That GitHub link, if you want to look at them at more detail, there are some links here and there. You want to check them later. My name is Jorge Aparicio, also known as Japaric on GitHub. Right now I'm a master's student at Luleå University of Technology, and I'm working with Professor Per Lindgren, and we do research on real-time system, and we are using Rust for our research. Today I will talk about concurrency in microcontrollers. So the agenda for this talk is to go through microcontrollers basics, and then cover cooperative multitasking, and then go into preemption as an alternative for doing multitasking. And we'll talk about the problems that arise from using preemption as a multitasking mechanism. And then we'll talk about locks as a way to solve those problems. Then I'll present a fearless concurrency framework we have been developing. And I conclude on some future work in this space. First, microcontrollers. So we have these single core devices with very small amount of RAM and few processing power. So why would you want to use a microcontroller in your application? The main reason is you want to do I/O with the world. So when you are working with general purpose computers, I/O means files, sockets, and databases. And when you're working with microcontrollers, I/O means reading sensors, controlling motors. Some of you also may know that you can use single-board computers like the Raspberry Pi to do this kind of I/O. So why would you pick a microcontroller instead of a Raspberry Pi, which is more powerful and runs an operating system like Linux? So within those reasons, we have that microcontrollers are cheaper, which is good for business. They are simpler systems. So they are simple enough that you can program them from scratch. They also have lower power consumption, which is good for battery life. Most importantly, you can have full control over how tasks get scheduled on this system if you're not using an operating system. And this is important if you have attribute at the top, which means that the standard library is not available in this program. Then we have another Rust program. We have this newest attribute at the top, which means that the standard library is not available in this program. Then we have another Rust program. We have this newest attribute at the top, which means that the standard library is not available in this program. Then we have some crates that will care of booting the device. Then you have your standard. You can only run one program at a time, and this program must never end. So in this case, when the main function returns, you will put your microcontroller to sleep. This quick start framework gives you this common 14T2-RISC-V microcontrollers. And currently it supports Cortex-M and MSP430 microcontrollers, and someone is already working on porting T2-RISC-V microcontrollers. A special region of memory called peripheral memory. So this program does two write operations, and the first one will turn an LED on, and the second one will turn it off. This approach to I/O is called memory map I/O. Purpose input-output is on and off, and express. Another peripheral alarm method works. So this timer, you can read these titles using usually Paul means shifts. It will using generators, serial interface using generators. So it looks similar to the PWA method I showed you before, but the condition is generator, so you can see that generators can on or off a macro per task. Note that you need to execute. It has busy waiting when the process cycles. Use example. And the second task, this timing constraint is satisfied using cooperative multitasking, and to be run at least twice. And if it's instant, and then you can receive. Microcontrollers provide a hardware mechanism. So how do they? At some point, they use one of the previous an interrupt handler memory bit that will run into the main function. And the interrupt, if the main function is so to speak, the duration of this, and the answer is it depends. And in that case, we cannot answer. So run is memory handler from Cortex and divide the interrupt. Safe code in them. Instead, we like to write just safe Rust code and have the compiler enforce the memory safety for us. And that's what basically is given side of and a list of the resources it has access to this. And you can only have resources across interrupt disabled. This other version of a ring buffer, which has a single producer and a single consumer. In this case, you can kind of split your ring buffer into a producer and a consumer, and this.
Hi everyone, and welcome to the first video of the SuperDevs Fellowship. SuperDevs is a Solana bootcamp and a Rust bootcamp that I'm running. It had around 2,300 people who participated, and only 120 got in finally. I take a personal session with these 120 people every week, and this is week 1. The goal of SuperDevs is by the end of SuperDevs, someone becomes a good distributed systems engineer. They become decent at Solana, and the top 20 people who graduate from SuperDevs get a $2,500 stipend. This is the very first class of SuperDevs. We'll go through the orientation from Aditya, who leads Super Team in India, followed by a class by me on macros. If you have not done Rust Bootcamp 1 and Bootcamp 2 on YouTube by me, this will be a little hard to follow. So it's very specific companies, but again, big companies. If you've gone through the prerequisites, and also the class that we're covering today. Cargo running, why can't it just be a simple function? What's written over here is what gets printed over here. Like this and this are very, that is different from a return swap of, quantity underscore 1, quantity underscore 2. So, what would quantity underscore 1 be? B of
Utah Rust.
Like I might have an hour a day. I've heard to do it.
Killing all the here using Ackee, and so you take the camera. Learn about just tactic and it work a bit. Other actors hire. And the main loop is pretty simple. I've got a TCP listener that I bind to, and then I start listening on it in another task. This and it's kind of, I guess, discretionary on how granular you want to be. There's a couple in here where I should.
Nom, 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 nom. Hi folks, welcome back to another Crust of Rust. It's been a while since I've been. So Rust has these two complicated in and of themselves. Nom, 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 nom. Hi folks, welcome back to another Crust of Rust. It's been a while since last time, although if you're watching this recorded, I guess maybe it hasn't been, in which case, welcome immediately back. I've been trying to find, what are good next topics for Crust of Rust, and over the past couple of months, I've sort of been noodling with a couple of different ideas, and Send and Sync came up because, not because Send and Sync are all that complicated in and of themselves, but more so because they tend to cause a bunch of confusion, probably because people think they're more complicated than they really are, and so I wanted to have a video going through, at a high level, what are they for, but also dig into which types are send, which types are sync, and crucially, which types are not, because I think that's a good indicator of what they're really used for. I expect that this stream will probably be fairly short. There's not too much to talk about here, and so what I'll do is also some Q&A at the end, if you're watching this video. And without more ado, I think we'll just thread safety in the language, and specifically, they used to represent thread safety. These two traits, send and sync, that are used to describe thread safety in the language. And specifically, they used to represent thread safety at the type level. There are all sorts of other languages where there are checks for whether you are doing something concurrently that you're not allowed to. The first one that comes to mind here, of course, is in Java collections. If you try to iterate over a collection while you're also modifying it, you get this concurrent modification exception. And it's a good example of the language at runtime catching if you're doing something that's probably wrong. However, in many cases, it's really just documentation that tells you whether or not it's okay for a given value or a given type to be used either across thread boundaries or used by multiple threads at the same time. In Rust, those concepts are all baked into the type system, so that at least in most cases, you can check for the thread safety and the correctness in terms of thread safety of your program just by type checking it. The two traits are very related, but they do serve different purposes. Like you couldn't really get away with just one or the other. And before I talk about how they differ, I want to talk about how they are the same. So first of all, they are both marker traits. You'll see that send is in the std marker module, and same thing for sync. Now markers, if we go over to the marker module, this talks about primitive traits and types representing basic properties of types. And what you see if you look through these is that all of these marker traits are specifically traits with no methods, hence the name marker. They're only used to mark that a type meets a given property or has a particular property or guarantee about it, but it does not confer any additional behavior. Like for example, if something implements a send trait, you don't get a sort of send method on it. That's not a thing. It just tells you that type is send. Marker traits are a little bit special, or has a particular property or guarantee, hence the name marker. They're only used to mark that a type meets a given property or has a particular property or guarantee about it, but it does not confer any additional behavior. Like for example, if something implements a send trait, you don't get a sort of send method on it. That's not a thing. It just tells you that type is send. Marker traits are a little bit special as far as the compiler is concerned too. So if we dig into the source here, you'll see that it is marked as an auto trait. This is not directly combined with the fact that it's a marker trait. Like you can have, not all marker traits are auto traits, but the fact that it's an auto trait means that the compiler will automatically implement this trait for you if all of the members of a type are themselves that same trait. So in the case of send, for example, if you define a new type, whether it's an enum or a struct or a type alias, that type will be send. Well, type alias is a little different, but let's take structs and enums or tuples and arrays and whatnot. They implement send if all of the types that are inside of it also implement send. Same thing for sync. These are auto traits. And you can sort of imagine that it would be weird to have an auto trait that is not a marker trait, because an auto trait implicitly is implemented for anything. It would be weird to have an auto trait that is not a marker trait, because an auto trait implicitly is implemented for anything where all the members implement the trait, but it's not clear what you would put in, like if there was a method you had to implement there, how you would delegate that to the inner types. So in general, all auto traits are marker traits, but not all marker traits are auto traits. Yeah, the empty comment here is very helpful. Thanks. So those are the ways in which they're the same. They're both marker traits. They're both auto traits. And apart from that, they sort of work the same way as all other traits. They're primarily used in trait bounds. So that would be, you can have a function or a method or something, or even just a type that requires that an argument that is passed or a field that it has or something is generic over must be safe to cross thread boundaries. And so that gets us to, how are they different? And we'll talk about send first, because it's easier to explain sync in terms of send than the other way around. The property that send tells you about a type is that it's okay to pass that value to another thread. So specifically, that is give away ownership of this thing to some other thread. So that thread from that point forward gets to do whatever it wants with that value. It sort of confers that it's not just that thread gets to read or gets to write. It's that thread can do whatever it wants to the value is the way to think about send. And most types are send, just like in general. The idea being that, if you have a primitive type, for example, if you have a Boolean or a number or something, giving it away to another thread has no downsides. Like, there's no problem handing that value to another thread because it's just a number, it's just a Boolean, it's just a string. The kind of things that are not send are more around types where if you pass them to another thread, then that thread might violate some implicit assumption or invariant of the underlying type. And there are two primary examples of this. RC, so the non-atomic reference counted type, and we'll get into why that's a problem. And the other one that comes up a fair amount is mutex guards. And that applies both to the standard mutex, but also to RW lock. This is not a universal property of like any is mutex guards, atomic reference counted type, and we'll get into why that's a problem. And the other one that comes up a fair amount is mutex guards. And that applies both to the standard mutex, but also to RW lock. This is not a universal property of like any mutex, but specifically the ones that are in the standard library that are backed by the OS implementation of these are usually so they're not send because there's a requirement, at least on certain operating systems, that the thread that gets the lock has to be the same thread that releases the lock. So if you take a lock on thread A, you're not allowed to then have thread B try to release the lock that A got. It has to be A that releases that lock. And notice that this doesn't mean that the mutex type itself isn't send. It doesn't mean that RW lock is not send. It's specifically the guard that's not send. And this is an example of a more general property, which is if you have the drop implementation of a type refer to a thread local state that was created as part of the creation of the object, then that generally means the type can't be send, right? Because imagine, you create this object on thread A and it uses thread local state on A. And then you send it to thread B, and then thread B tries to drop it. It goes out of scope or whatever. Then when thread B drops it, if the drop tries to access that same thread local state, it's going to try to access B's thread local state, not A's, even though A is what it used in order to create the object. And therefore, you end up sort of violating some internal invariant, and that usually doesn't go very well. RC is a little bit of a different beast. The reason why RC isn't send is because I can write code that, in fact, let me, cargo new lib, what are we going to call this one? Sharing is caring. So if I go in here, I'll get rid of some of this. No, I mean actual thread locals, like, the thread local macro from the standard library. So the problem with RC, in fact, let's just make our own RC. This is roughly what RC looks like. There is a box of an inner of T. And there's a, oops, nope. To show the inner is going to be RC implement. Do this. So when we drop it, if the current count is 1, then we're going to drop the inner thing from raw self.inner. And that's also unsafe. And finally, we implement ops deref for RCT. I'm going to talk to this a little bit more in a second. PSR mute, this has to be an unsafe cell. There are a bunch of things that I'm sort of skimming over here. It's a sort of mutual exclusion by the fact that one thread can only be doing one thing at one time. So that's the reason why this access is safe. And it's also the reason why this can just be a standard use source lib to source main, the closure that you pass to spawn. And you will almost clear because star mute should not implement send. Explicitly not implement send. Give me 1 second here, because this is real weird. Wait a second. Why is this allowing me to... this is a good way to just test whether a type constraint you expect actually works the way you want. So I'm going to take an x, which is going to be an RC of whatever, and it's going to call foo with x. Yeah. Okay, so our type isn't send, right? So what I'm doing here, right, is I create a function foo that requires its argument be send. I create a function bar that takes an RC, this is our RC type, and calls foo with that RC. And the compiler says, bar calling foo this way is not okay because RC of unit does not implement send, right? And so the error gives us more explanation here. It says star mute inner cannot be sent between threads safely, and specifically this is because it appears within RC, so the trait send is not implemented, and it's required by this bound in foo. But this should also not be okay. It might be because okay, I think it's just the compiler being particularly smart here and realizing that this thread doesn't actually use Y. I think that was what, like this, meant that it didn't even here. We do need to move it into the thread, but we also have a clone of that same RC in X. And now, okay, let's go back to this. I can remove our little foo bar business here. But yeah, so what we're doing here is we're attempting at least to move Y into this new thread, and we're just going to drop it, but we do need to move it into the thread. But we also have a clone of that same RC in X. And now, of course, these two threads both have a pointer to the same RC, to the same inner. And when we imagine that these two threads run concurrently, and they both try to drop Y, so they both try to drop what is effectively the same RC. So both threads enter drop for RC at the same time. They both read the count. Then you might end up with neither of them seeing the other one's decrement yet, because they're running concurrently, right? So they both, here, when they dereference the count, they might both see 2, not 1. So neither of them go into this. They both go in here, they both decrement the count by 1 each, so it's now 0, but neither of them took this to actually drop. The send is valuable, right? It tells the compiler that this time spec here is also RC. All right, so in other words, this is why RC can't be sent. Very different reason for why mutex guard can't be send, but this is the reason it can't be send. So let's then move on to sync. So sync is fairly related to send. In fact, they're so related that sync is almost defined in terms of send. So specifically, a type T is sync if and only if a reference to T is send. So let's try to digest that a little bit. If you have a type where a reference to that type is allowed to be shared across threads, then that type is sync, even if the type itself cannot be passed to some other thread. Like I can't give you a mutex guard, but if I have a mutex guard, I can give you a reference to sync, even if the type itself cannot be passed to some other thread. Like I can't give you a mutex guard, but if I have a mutex guard, I can give you a reference to that mutex guard. That's fine, right? Because, and this sort of and the reason this distinction is important, this comes back to the reason why mutex guard can't be send, right? Is that we can't allow some other thread to drop it. But if we just give away a shared reference to one that we already have, they're not going to drop it for us, right? They don't get any kind of owned access to that mutex guard. They can't drop it because it's behind a shared reference, and dropping requires a mutable reference. They can't do like tricks with mem replace or anything because all of those require a mutable reference to the inner type. All they can do is read from it, which is all fine. None of that means that they drop, which is the thing that we were concerned about. However, RC can't be sync, right? So it's the same kind of problem. If RC was sync, then what I could do is I could take a reference to an RC, give that reference to another thread, and then that other thread just calls clone on it. And we know that the clone implementation also requires that all access happens on one thread. So that is why RC is not send and not sync, whereas a mutex guard is not send, but it is sync. RC is not send and not sync, whereas a mutex guard is not send, but it is sync. No, when I say shared reference, I mean an actual reference. Like I mean the, this type, an actual shared reference. When I say mutable reference, I mean this. So mutex guard is not send, but it is sync. RC is not send and not sync. Which might make you wonder, okay, are there types that are send but not sync? And there are. The primary examples of this are the interior mutability types. So things like cell and ref cell. And cell is a really interesting example. So the basic idea of cell is that it doesn't give out references to the inner type. So you can have a cell of T, and the things that you can do with a cell of T are you can create a new one by giving an old value. You can replace its value. You can extract its value, but again, by value, only by consuming self. And there's nothing in here that allows you to get a reference to the value that's inside of the cell. And the reason why this is okay is because on any single thread, right? Imagine you're on a single thread here. If the value is encapsulated inside of there and you never give out a reference to it, then at any given point in time, you know that you have exclusive access to the inner value. No one else has a reference to it because this doesn't give out references. And no other thread is currently executing on that value. So it's okay to, again, this ties back to the fact that this type is not sync, right? So no other thread has a shared reference to this type, and you haven't given out any shared references to the value that's inside of this. So therefore, you are the only one with access to the thing inside the cell whenever you are executing. And therefore, you're allowed to modify the value that's inside there because you effectively have exclusive access. No other thread's accessing, and the current thread is you. And so that's why you can safely mutate the inside of a cell, even though you only have a shared reference. But again, it relies on the fact that cell is not sync. But it is send though, right? Because again, you haven't given out any references. So if you give away a cell to another thread, there's nothing left on this thread that might interfere with that thread modifying the value, right? If I have a cell and I give it away to you, I cannot possibly have any references to the cell because then I wouldn't be allowed to move it, or to the stuff inside the cell because there are no accessors that give out a shared reference in the first place. And so sending it, totally fine. The moment I send it, that other thread is free to do things like modify the inner value because it can rely on the same invariant, right? That no one else has a shared reference to the cell, as in no other thread. And on this thread, any shared reference to the cell is not currently executing because there's only one thread involved. Not demand what the inner type. You don't need that requirement because, if you're exploring a single thread shared reference. The reason you sometimes see it through RC